Hello and welcome to another geometry read-along. Today we will be tackling section 2.2 on polygons and circles. First up, the applied problem to introduce the topic. Here we have a box end wrench, that is to say a wrench in which the end is entirely enclosed, has a 6-point opening on one end. What is the name of the polygonal opening? And why would this shape be used? So can we not only name the shape we see inside here, but why would that shape in particular be a good one to pick versus all the other possible shapes? Keep that in mind as we go through the section. So first up, triangles. Many geometric figures made up of line segments can be described by the lengths of their segments or by the measures of the angles formed. The simplest of these figures is the triangle. Given three non-collinear points, A, B, and C, the triangle determined by these 3 points, written triangle ABC, is formed by the sides segment AB, segment AC, and segment BC. Again, this is the very technical version of something you probably already intuitively understand. You make 3 dots, you connect the dots, you have a triangle. A triangle has 3 angles and 3 sides. That's probably the most useful definitional, but again, this is more the technical definition here, just for comparison, right? And the technical part can become important when we get into the nitty-gritty details, and those become apparent in later proofs and theorems. Furthermore, we can classify triangles by both the lengths of their sides and the measures of their angles. We have defined many special triangles next. Figure 2.25 shows an example of each of them. So here in this table, I would include all of these in your notes. We have the equilateral, isosceles, and scalene. Those are the sides. And we have the acute, right, obtuse, and equal angular. And those are classifying by angles. You have the definition right there, which is the same as it's been since grade school. And then a pictorial example to go along with each of those. Here is the equilateral as marked with the equal sides. The isosceles triangle, scalene, no marks on any sides. Acute, right, obtuse, and equal angular as marked there. And of course, we know that the equilateral and the equal angular are in fact the same figure. But that's a theorem that'll come up later. All right, special features. In an isosceles triangle, the angle opposite the congruent sides is called, the angles opposite congruent sides are called base angles. Okay, highlight there. Base angles. And the sides between the 2 angles is usually called the base of the triangle. Okay, so oftentimes we will refer to the base of a triangle, such as if you want to find the area, you do base times height, and it's always in reference to whatever is the bottom side, what looks like sitting on the ground. But for an isosceles, since we have these 2 are the same and this one is the odd man out, we refer to this as the base side, and these would be the base angles, right, across from those 2 congruent sides, right? Oh, as I said here, right? Figure 2.26, the base angles are A and C, and the base is segment AC. The angle between the 2 congruent sides is often called the vertex angle. Okay, the angle between the congruent sides is the vertex angle, so that would be this one right here. Figure 226A, angle B is the vertex angle. Notice that because an isosceles triangle has at least 2 sides congruent Any equilateral triangle can also be classified as an isosceles triangle. It's that at least part. They didn't say exactly 2, at least 2. 3 is at least 2. Oh, yeah, I guess you're technically correct, right? That's what we're all about here. Technically correct is the best kind of correct. In a right triangle, the side opposite the right angle is called the hypotenuse, and the other two shorter sides are called the legs of the triangle. Okay, opposite right angle is the hypotenuse, other two short sides are the legs. Okay. In figure 226b, segment AC and segment BC, right there, are legs, and segment AB is the hypotenuse of right triangle, triangle ABC. Why'd they had to say triangle twice? I don't know. In general, we use more than one of the terms just defined to describe a triangle. For example, a triangle with two congruent sides and a right angle is called an isosceles right triangle because it fulfills both requirements. Figure 226C shows a right isosceles triangle, triangle ABC. So here we have the two congruent legs, notice the markings there, and the right angle here. A triangle with one right angle, but with no two sides congruent, is called a right scalene triangle. 226B is an example of that. We will show in Chapter 4 that every equilateral triangle is also equiangular and vice versa, something I mentioned earlier. There you go. Something to look forward to. Okay. Simple closed curves. Triangles are part of a more general class of geometric figures called simple closed curves. In fact, this is probably the most general class. A simple closed curve is a figure that lies in a plane, so you can draw it on a sheet of paper, and can be traced, drawn with the pencil, right, so that the starting and ending points are the same. Okay, so you loop back to where you started, and no part of the curve is crossed or retraced. So I will go ahead and highlight there, add that definition to your notes. And we've got some examples and non-examples shown here. So simple closed curves. I start here, draw all the way around, come back. It works. This one, start here, go around, come back. I crossed over here. Okay? Any crisscross, even though it makes a great Mario Kart track, this would not be a simple closed curve. Not sure if that would make it like a complex closed curve. I don't know what the next stage term would be. But I can tell you, at least closed, right? That is an open curve, right? It's not closed. The closed part, if I may, let's use red here, right? The closed part is the starting and ending points are the same part, okay? And then the simple part refers to the no crossover or retracing, okay? And even though it says curve, all straight lines are very special versions of curves. So even though it's all made of segments, it is still a simple closed curve. This one requires you to retrace at some point to do this bit, and then come back to do this bit. Okay, next up, a circle is a simple closed curve that consists of the set of all points equidistant from a given point. Equal distance, okay? So there is your formal definition. And just to review, remember, any line is already a set of all points, right, in an infinite direction. So we're already used to that. Well, it looks like a curve. I drew a thing. Yeah, you drew the set of all points in a single direction. This is the set of all points that are a distance from a center. The center of the circle, right? A circle is named by its center. Circle O here is pictured in figure 228. So we got circle O. There it is. Then we got special parts of the circle. A line segment joining the center with a point on the circle is called a radius. Ooh, on the circle. Right? This is the circle. Everything in the middle is not part of the circle. The circle is only the figure around, it's only the edge, it's only the crust of the pizza, okay? The rest of the dough and the cheese and the sauce and the bit, that area inside the circle is not part of the circle itself. That would be a disk. So a line segment joining the center to a point on the circle is called the radius. Yep. Plural radii. So you pronounce both of those I's in two different ways. Radii. Funny old Latin. There you go. Circle. Its length is called the radius of the circle. A line segment containing the center with endpoints on the circle is called a diameter of the circle. All right. Its length is called the diameter of the circle. So those are both used to reference the measure and size of the circle. Notice that we use the words radius and diameter to refer to line segments as well as the lengths of those line segments. Mostly because we can draw many different radii. So you can't say the radius of the circle is 6 inches. Well, which one? Is it this one? Is it this one? Is it this one? They're all the same. In figure 228b, R, or segment OP, is a radius and D is a diameter when viewed as segments. We also say the radius of circle O is 6 inches and the diameter is 12 inches because those distances will always be the same no matter which way you actually draw your segments. Okay? That's circles. Polygons. As we can see in figure 227, simple closed curve need not be, quote, curved. Right, that was this example here. For example, a triangle is a simple closed curve composed of 3 line segments. In general, a polygon is a simple closed curve composed of line segments. Simple closed curve composed of line segments. So now you kind of see, this is a great example of the axiomatic system at work. Our definition of polygon now is so much shorter and simpler because we've already defined what a simple closed curve is. Right? We've established one category, and now this is a special case of that category. So each subsequent definition builds off of the prior definitions. Figure 229 shows some examples of polygons. So we've got 4-sider here. We've got this crazy, funky, lightning bolty thing. Hedgehog? I don't know. And this really nice, lovely little Pentagon shape there. Polygons are named by listing the vertices in order around the figure. For instance, we might name the polygon in 229A as ABCD. ABCD, or BCDA, BCDA, or DABC, DABC. Notice they've all gone clockwise. That's generally going to be the consensus, mostly clockwise direction there. 2 vertices that are endpoints of a side of a polygon are called adjacent vertices. Ooh. Good to know. Adjacent vertices are literally connected by a line segment. Thus, figure 229A, A and B are adjacent vertices, as are B and C, and so on and so forth. 2 sides of a polygon that share a vertex are called adjacent sides. Okay, so adjacent sides are literally connected to each other. Figure 229A, a segment AD, this one here, and DC are adjacent sides, as would be BC, CD, AB and BC, so on. Polygons are usually described by the number of sides they contain. We have listed some names of some common polygons next. Okay? So usually by the number of sides. So here we go. If these are not immediately obvious to you, you don't already have these memorized from grade school, put that in your notes and commit those names to memory. Triangle, quadrilateral, pentagon, hexagon, octagon, decagon, n-gon. That's just the general, any number n. By these definitions, in figure 229, ABCD is a quadrilateral, EFGHIJKL is an octagon, and PQRSTU is a hexagon. Notice that in a polygon, the number of vertices is the same as the number of sides. Ooh, that's good. Write that down. Number of vertices, the same as the number of sides. And in fact, for those of you interested, the term polygon comes from the Greek poly, meaning multiples, many, or number of, and gons actually refers to an angle. So polygon means multiple angles. So the term actually is technically a pentagon and hexagon are counting the number of angles or the vertices, the corners. They're not the number of sides originally, as the origin of the name. A little bit extra trivia for you. All right, quadrilaterals. Many quadrilaterals are named by the lengths of their sides, the measures of their angles, or some other attribute such as parallelism. We say that two lines are parallel if they are in the same plane and do not intersect. Okay, there you go. Definition of parallel. In the same plane, but don't intersect. Of course, in 3D space, you could have non-intersecting lines that are not in the same plane. Imagine like a line over here and a line, out here. That's, it looks like it crosses in front of, but then I just rotate this way. Oh yeah, they're totally missing, right? Those would be skew lines. The two line segments are parallel if the lines containing the segments are parallel. Two line segments are parallel if the lines containing the segments are parallel. Segment parallel is based on line parallel. Parallel lines are identified using one or more arrowheads in the middle of the lines. That's the little doodads here. In figure 2.30, lines L is parallel to line M, and we write L is parallel to M. Okay, so the symbol for parallelism is two vertical bars there. We describe several types of quadrilaterals next, and figure 231 displays an example of each type. Oh, so convenient. Again, here you go. Have the giant list in your notes for easy reference. We have the good old square, defined as all sides are congruent and all angles are right angles. These definitions, of course, the definition of the specific quadrilateral. So this is not from scratch. This is dependent on a quadrilateral that a square is a quadrilateral such that all sides are congruent and all angles are right angles. Okay? Rectangle, all angles are right angles. Rhombus, all sides are congruent. Parallelogram, opposite sides are parallel. Trapezoid, exactly one pair of sides is parallel. Go ahead and underline that. Exactly one pair. So a parallelogram has two pairs. Trapezoid has one pair. A parallelogram is not a special trapezoid, or vice versa. A trapezoid is not a special parallelogram. The isosceles trapezoid is a trapezoid in which the non-parallel sides are congruent, and a kite. There are two pairs of adjacent sides where the sides in each pair are congruent, but the pairs have no side in common. Two pairs of adjacent sides. Okay, so remember, adjacent sides are two things connected, so we got two pairs where the sides in each pair are congruent. So this is congruent to that, and this is congruent to that. We got the two pairs. But the pairs have no side in common. So I have two unique pairs. It's not that this pair is actually, but it's secretly that these two sides were the same the whole time. Right? It's not one of those. Can't have that. All right, here we go. There is the picture. So we'll go ahead and illustrate each of those definitions. The parallel sides in a trapezoid are called bases of the trapezoid. The sides that are not parallel are called the legs of the trapezoid. So right down here. Base and base, leg, leg. And even in the isosceles, base, base, leg, leg. Thus, in each trapezoid, in figure 231, the bases of the trapezoid are indicated by the parallel line marks. The other two sides are the legs. I really ought to just read the thing myself before comment ahead of time. You may have noticed that there is some overlap in the definitions. That's by design. For example, every square is also a rectangle because a square has 4 right angles. We will explore several other such relationships in the problem set and in Chapter 5. All right. Big geometry concept right here. Overall applies to everything. We're going to need this. It's going to come in super duper handy. Symmetry. We have seen that we can describe polygons in terms of the number of sides they have, or in terms of attributes of their sides and angles. Also, we can use symmetries of various types to describe polygons. There are 2 common types of symmetry in a geometric figure may possess: reflection symmetry and rotation symmetry. Think about that for a moment before reading ahead. Reflection symmetry versus rotation symmetry. What do you think it's going to require? A figure has reflection symmetry if there is a line along which the figure may be folded so that one half of the figure matches exactly with the other half. Okay? It would be nice if we could have some like purely abstract definitions that exist in pure mental space and do not rely on any concepts of physical properties. But alas, it is much easier to define symmetry as if you were to create the figure on actual paper, cut it out with scissors, and literally fold it in half. And if everything lines up, it's reflectional symmetry. The folded line is called the line of symmetry or the axis of symmetry. Okay. So, the isosceles triangle shown in 232a, that'll be right down here, has reflection symmetry because if we fold it along the axis of symmetry, right there, the 2 portions of the triangle will match exactly. And unfortunately, my digital tools here do not let me flip something over. All I can do is rotate them around, so I cannot demonstrate that with a digital drawing here. But I think you can imagine the thing here. We cut this out, fold it in half, right? A figure can have more than one axis of symmetry, as the fold lines for the square in 232b and the equilateral triangle in 232c demonstrate. So here we got 4 axes. Okay, remember goes the line all the way through, not just the ray from the center. This is 4 lines of symmetry, not 8. And this equilateral triangle has 3 axes of symmetry. The triangle in 232D has no line of symmetry. Oh, poor scalene triangle. No reflection symmetry. If there is no line that divides it perfectly in half so that each half is a mirror of the other, again, reflections come from a mirror, so imagine you see the mirror image of one side on the other side. That would be an axis. If there is no way to draw such a line, then there is no reflection symmetry. Now, because an isosceles triangle has reflection symmetry, we can establish a relationship between its base angles. When the triangle in 232A is folded along the axis of symmetry, the base angles will match. This means that these 2 angles have the same measure. We usually state this result as base angles of an isosceles triangle are congruent. That is an important conclusion to keep in mind. Isosceles triangle, by definition, has the 2 sides that are congruent, and also by nature of symmetry, the 2 base angles are also congruent. An equilateral triangle is a special type of isosceles triangle, so it also has base angles congruent. But an equilateral triangle has 3 axes of symmetry, 1 through each vertex. See the figure beforehand. Thus, any 2 angles of the equilateral triangle will have the same measure. So the angle A equals angle B, and angle B is equal to angle C, and C is back equal to A. Any 2 pairs will be congruent. This means an equilateral triangle is also an equiangular. We discuss these angle relationships more formally in Chapter 4, and that's where we will take this thought process and again formalize it into a proper, rigorous proof that no one can poke any possible holes in. But what about, technically, but, right? We got to get technically correct with it. That's what a proof is for. Something to look forward to. A geometric figure has rotation symmetry if the figure can be rotated about a point less than a full turn. Okay? So exactly as we would expect, rotational symmetry rotates the figure, spins it around. It only counts if it's less than a full turn. If you turn it all the way around back to the starting point, you didn't symmetry anything. So that the image is identical to the original form. Okay? Turn it to where it's identical. The point is called the center of rotation symmetry. Right? Rotate it about a point. So again, take your physical thing on paper, stick your finger somewhere in the middle so that you hold it down right there, and then you spin it around. Okay? That's the point where your finger is holding, is the center of rotation. Okay? And you rotate the thing around until it looks the same. That I can definitely do digitally here. And use my tool here, and I get a little rotation. So notice where my little rotation tool grabber is. It's on the right hand side, and I rotate this around, and the triangle matches up. Oh, I kind of shifted off to the side there. I didn't perfectly center it, right? But I haven't gone all the way around, and yet I match up still. That's rotational symmetry. Okay. The equilateral triangle in figure 233 has rotational symmetry because it can be rotated through an angle of, in this case, 120 degrees, 1/3 of a full turn. Remember, it's 360 all the way around. And the image will match exactly with the original triangle. The equilateral triangle also has a rotation symmetry of 240 degrees, right? Because I could rotate it again the same way. So an equilateral triangle has 2 rotation symmetries. That's a good conclusion to remember. Equilateral triangle has 2 rotation symmetries. Okay? All right. The trapezoid in figure 234, right here, does not have rotation symmetry because it must be rotated through 1 full turn of 360 degrees before the image will match the original figure. And this is a technical bit here. While we are moving the thing, the new transformed, the rotated bit is called an image of the figure, so not to be confused. So when I trace it to rotate it, this blue outline is called the image of the figure. It looks just like the figure, except I'm doing weird, funky things with it, and it never quite matches up until I get all the way around. We can test figures for both reflection and rotation symmetries. To test for reflection symmetry, try folding the figure in half. To test for rotation symmetry, trace a copy of the figure and try to superimpose the tracing on the original figure by rotating it about a point. Okay? Again, they rely on a physical element, and I understand that can be a little tough to do digitally in all mediums. So here is an excellent example in real life. Quilters construct quilts by starting with a single square block and then stitching many identical blocks together to form a finished quilt with an eye-pleasing pattern, or sometimes non-identical squares. Traditional quilt blocks often incorporate geometric shapes and exhibit reflection and or rotation symmetry. 3 different quilt block patterns are shown in figure 235. Describe as completely as possible the geometric shapes that make up each pattern and the symmetries of the block. Okay? So first identify all of these shapes that you can see. Oh, I got a triangle here, a rectangle there, square, square, triangle, right? And all of the possible symmetries. Can I rotate this around? And in this case, notice the shading of the blocks that will affect, for example, rotational symmetry. Okay? If I draw just some of this in, like that, and I have shading in these sections, okay, but not in these sections, when I take this whole thing and rotate it. Notice my shading now lands in the empty space instead of in the shaded area. So this is not a rotational symmetry. 90-degree turn did not actually match up, even if the shapes otherwise would have matched. The shading is also an important factor here. So, quilt block A is made up of rectangles. You can see some right there and there. Right isosceles triangles. That would be the little guys in the corners. And hexagons. That's this funky little diamondy crystal shape there. Okay, it looks like a Zelda rupee. It has both reflection and rotation symmetry. I could definitely fold this in half, probably this way, this way, this way, this way. Lots of symmetry. And I could spin it around 90 degrees. Yeah, 4 lines of symmetry. 1, 2, 3, 4, just like regular square. And 3 rotations between 0 and 360 around the center of the square, through which the block may be turned to match the original. 90, 180, and 270. We say this block has 3 rotation symmetries. Okay? The 4th rotation gets it right back to where it started, so that doesn't count. Okay? So you might want to say it sounds like it would be more convenient if, hey, it's a 4-sided figure, a single plane square by itself. I can rotate it 4 times and every time it will match up, but that last one doesn't count, so it's always 1 less than, say, the sides of the figure if it matches. B. The large triangles in the quilt block are right scalene triangles. So that'd be large triangles would be these guys here. Okay. The smallest triangles are right isosceles triangles. That'd be the little ones in the center. And the long, narrow triangles are acute isosceles triangles. The figure has both reflection and rotation symmetry. There are 2 axes of reflection symmetry, namely the 2 diagonals, and 1 rotation symmetry of 180 degrees. So to see that, let's give my trace here another 90-degree turn. And there we can see the shading will match up, and if I added in the triangles, those would have matched up. And again, we will have to go through the diagonal there in order to actually fold it and have everything, including the shading, match up, because we can clearly see that from left to right, or simply from top to bottom, the shading parts are going to be mismatched. It will not be a perfect symmetry. Finally, quilt block C is made up of squares and right isosceles triangles. So we've got squares here and then right isosceles triangles, and it's not super evident, but you could create a stitch inside here and divide this pinwheel shape up into squares and triangles, and that is in fact how they would have composed this were this a real quilt square. But unfortunately it has no reflection symmetry because of that off nature. This is going that way, that goes this way, and so I get no perfect reflections. But it does have 3-fold rotation symmetry of 90, 180, and 270 degrees. Now that brings us to the wrench. So, now we know that the opening of the wrench has 6 sides, so it is a hexagon. The wrench thus has 6 rotational symmetries and fix a hexagonal bolt in any of 6 positions, each 60 degrees apart. That is the advantage. If you had, say, a square opening wrench, okay, you would have to, right, pick it up and reposition, fit it over the wrench every 90 degrees. You would have to be able to rotate that full rotation, right? Pick it up, and you can go this way, and then pick it up and go this way, right? Whereas with the 60 degrees, you can turn, if you had to, if in really tight squeezy spaces, fitting it between something, I can barely get in there, you can go right, a little bit at a time. You can rotate 60 degrees at a time and reapply the wrench each time. So that's the advantage. But of course, you can't go too far, because if you add too many sides, we start to approximate a circle, and with a circle, you would just slip and spin freely, and you wouldn't actually be able to turn anything. So that's why the hexagon is the best compromise there. Another great application of polygons here. Excellent example of the Pentagon is the Pentagon. Who names these things? In Arlington, Virginia, home to the U.S. Department of Defense. This building has the largest ground area of any office building in the world. Ground area, right? Not total floor space. Ground area. Because it's low and flat. It's not a skyscraper tower. Each of the outer sides of the Pentagon measures 921 feet, and it covers an area of 1,263,240 square feet. That's a big Pentagon. Each day, 26,000 people work in the building and travel along its 17 miles of hallways. Because you can just kind of see from this, you've got layers and layers of hall all the way around, and then next in, and it's just spiraling into the center there. That's a lot of hallway. All right, there you go. Polygons and circles and symmetry all coming at you in this section. What a wonderful piece of geometry. I hope that helped. Enjoy the rest of your day.